So our next speaker is going to talk about Bayesian supervised domain adaptation for short text similarity. And the presenter will be Arafat Sultan.
Hello, hello everyone. Welcome. I will present a study on domain adaptation for short text semantic similarity. My name is Arafat, and this was a joint work with Jordan Boyd-Graber and Tammy Sumner at University of Colorado. This is a brief outline of the talk, brief overview of the talk. I'll first explain the task of short text similarity, or STS, and how it can be applied to the more practical real-life tasks of question answering and short answer grading. I'll then briefly discuss Bayesian regression models for these tasks, which we then extend for domain adaptation. Finally, I'll present our experiments and results. So here's an example of the task of short text similarity, or STS. So given two short text snippets, most of the time sentences, the task is to compute a score that represents the degree of their semantic similarity. So these are examples of human annotations of short text similarity taken from the semi-eval STS task. So given such annotations, the goal for a model is to learn to compute such scores. So how is this task useful? Let me give you an example in question answering. So this task is known as answer sentence ranking or answer sentence selection. Here, given a question and a set of candidate answer sentences, the goal is to rank those sentences so that the ones that contain an answer are ranked higher. And most existing systems solve this problem by computing the semantic similarity between the question and each of these answer sentence candidates and ranking them based on that score. So in this example, as you can see, sentence 1 within that red box actually contains an answer to the question, and that's why the rank of sentence 1 is higher. So high ranks are represented by low numbers, right? Okay. So here's another example. This is short answer grading. In this task, in addition to the question, there is also a reference answer. So the task is to compute, the task is to grade the answers, but the way it is done is by computing computing a semantic similarity score with the between the student answer and the reference answer. The higher the similarity, the higher the grade. Okay, so given all that, this is what kind of motivates our study. So STS algorithms, like many other NLP algorithms, have applications in all these different domains and downstream tasks. So we wanted to build a model that can learn from annotations from all these domains, but can still fine-tune its behavior to a given domain, given some annotations from that particular domain. So I'll explain in a while. So, but before we go there, let's first see the Bayesian linear regression models that we then later extend for domain adaptation. So this is a simple linear regression model for the task of STS. S here represents the semantic similarity between the two sentences, and it is just a weighted sum of the features. F is the feature vector, W is the weight vector, and given labels, label data, the task is to compute the weight vector from the training data set, right? And this simple architecture has actually been proved very successful at the semi-eval STS task over different years of the task. And the features that have been used for this task ranges from average word similarity between the two sentences and similarities in their syntactic structures and so on. This model is actually directly applicable to the task of short answer grading too, because there also we compute a real valued score that represents how good the answer is. But for question answer ranking, the annotations are not real valued, but they are actually binary. So the annotators mention whether the given candidate answer sentence actually answers the question or not. So given that, what we learned in this, so it has the same setup. You still have the feature vector and the weight vector, but the weighted sum of the features here is actually the logit, which represents the probability that that sentence contains an answer to the question. But you still use that same weighted sum of features. Okay, so these were two applications. So we use a common feature set for STS as well as the two applications. This feature set is taken from last year's semi-eval weighting system. It is a very simple system. It has only two features. The first one is the degree of, the first one is derived first by aligning the two, aligning words in the two sentences, and this alignment is done by looking at the semantic similarity between pairs in across the two sentences and the similarities in their context, like in the context they occur in the two sentences. And from the output of the aligner, then the degree of content word alignment between the two sentences is used as a measure of semantic similarity, and that's the first feature here. And the second feature is derived from pre-trained word embeddings. So each sentence is represented by just the sum of the content word embeddings in that sentence, and then the cosine similarity between the two sentences is taken as another measure of similarity. So these are the two features used in that system. We just wanted to see how this system performs on all three tasks. We already knew that it performs well in STS, but I'll not get into the details here, but the summary is that it actually performs at least as well as the state of the art on all three tasks, the then state of the art. Okay, so this is an extension of the linear Bayes STS model for domain adaptation. What we have here is still, semantic similarity is still computed as a weighted sum of the features, but for each domain here for which we have labeled data, we learn a specific, a domain-specific vector WD. So for each domain we have this vector, and each of these WDs has a Gaussian prior, which is centered at W star, which W star here is a common weight vector across all the domains. So as you can see from the diagram, the likelihood and hence the posterior of W star actually depends on all annotations from all the domains, and each WD for each domain follows that distribution of W star, but only to the extent that is permitted by observations in that particular domain. So at test time, given a sentence pair from a target domain, the weight vector in that domain is actually applied to the computation of semantic similarity. Okay, so this is not a new model. Very similar models have been applied to tasks such as named entity recognition or dependency parsing before. We wanted to see how this works, how well this works on semantic similarity, and here are the results. So I'm showing three results from three different models here. The black curve shows the performance of a basic linear regression model if you train it on annotations from all domains. The red curve shows the same model but trained on only in domain annotations, and the green curve shows the domain the adaptive model. The metric here is average correlation with human annotations across 10 different domains. So the domains in our experiments were, for example, forum question and answers, image captions, news headlines, and so on. And so as you can see here, so on the x-axis I'm showing a number of training pairs per domain, and as you can see, the in-domain model does better as the number of training pairs grows, and the global model does relatively worse as we have more training data. But what's interesting is that, and what's important is that the adaptive model actually performs well across all different training, all different amounts of training examples. Although as expected, the in-domain model actually catches up with more training data later. Okay, this I'm going to skip for now, and we'll come back if we have time later. So then we wanted to see how this model performs on multitask learning. So the setup here is that we now want to extend, so within the Bayesian hierarchy, we want to add one more level so that we can build a single model for all three tasks, and so that this model can adapt to the requirements of all these tasks. And in the setup, we for each task, we actually have multiple domains. So what we are trying to train here is a single model that can tune its behavior to a particular a task domain pair. So this is the model. It is just a bigger model, but conceptually it's just one more. It is just adding one more level to the hierarchy. So now we have, in addition to the domain-specific weight vectors, we now have task-specific vectors. So each domain in a task has a Gaussian prior centered at the task level weight vector, and all these task level weight vectors have their center at W star. So basically the same idea, just extended one more level for to deal with all these tasks. Okay, so now I'll show the results. So these are results from STS. You can see similar patterns that we saw with the domain adaptation model within STS, and that is true for short answer grading too. But for answer sentence ranking, we saw something different. So here the global model actually performs better than the in-domain model, and our experiments showed that the reason why this happens is that the annotations in the answer sentence ranking task, they are binary, as I have already mentioned, and the finer grained short text similarity and grading annotations actually help the model more than the in-domain but coarser grained answer sentence ranking annotations. But as you can see, the adaptive model suffers for that a little, but still it is very close to the best model here. So across all three tasks, if we have to choose a model, it's the adaptive model in our experiments. So yes, those are the findings from our experiments. First of all, it improves performance when, especially when in-domain data is scarce, and then it actually performs across the board better than the other two models. These are some. There has not been much work on domain adaptation for short text similarity. These are some examples. I will not get into the details, but what is important is that these studies did not compare the adaptive model with a comparable Bayes model that's not adaptive. This is the first time, to the best of our knowledge, that this has been done. And as future work, we are interested in these. So first of all, our system had only 2 features. So since systems with more features tend to do well on with in-domain annotations, we'd like to see how adding features changes the behavior of the system, if it changes that. And also we would like to, semantic similarity has many other applications. We'd like to see how it behaves on other applications. And also our model was supervised, so it assumes in-domain annotations for the target domain. So we could also try semi and unsupervised adaptation models where no such assumptions are made. Okay, this is some references, and that's that. Thank you.
Questions?
So in your graphs, you had the comparison between the red line for individuals, for individual domains, and compared to both the global and adaptive models.
Yes.
So my question is that why do you think that the training on the same domain, if I understood correctly by the individual word, individual means same domain, training data,
Yes.
right?
Yes.
Why is it not good when we have few data?
So, yeah, so with so here what you are seeing is the amount of training data available per domain. So what is happening is that the in-domain model is only using that data.
Okay, so it's before filtration.
Sorry?
So for example, you had 20 training data in total, and then you
Not in total, per domain. So the in-domain model is only using those 20 instances,
Okay.
but the other two models are using more.
Right, okay, thank you.
More questions?
How do you deal with domains that are not in training data?
So in our case, it was supervised adaptation, but one thing that you can do if you do not have label data in the target domain is that is to use, let me go back to, is to use the common weight vector across all domains, which, yeah, that's always an option, but it does not, we do not expect to see similar behavior with that weight vector.
Thank you.
Hi. So your domain adaptation is specifically for short text. Did you see any difference in performance for long text if you tried those experiments?
Okay, I don't know like what kind of results we can expect to see. So first of all, for long text, you will see other types of features mostly. So yeah, without doing any experiments, it's difficult to kind of predict how what results you would see.
Cool, thanks.
But yeah, this is for short text only.
We have time for more questions.
Thank you. You choose two kind of features, and word embeddings and another one. And what do you think which is more informative for this?
Which is more informative?
No, I mean if we take only second one embeddings, does it
Yeah,
much less or not?
Yeah, so what we showed in our original paper from last year's Semival STS paper is that for the Semival dataset, the alignment feature is more informative. And with only the embedding features, it does not do as well. I mean, both features contribute to its performance, but if you have to pick one feature, that would be the alignment feature.
Did you remove the stop words from your sentences before doing
I did,
this?
yes.
And when you use a stop word, what result did you get?
That experiment I did a long time ago, but yeah, it gets worse with stop words. Yeah.
We have time for one more question. So I have one question. So it seems like this is a very small data scenario, right? Is that true?
Thousands, yes.
So, and per domain you have like only few hundred examples.
Yes.
So will this work in a large data scenario at all? What's your intuition?
So here we can already see that with like 300 or maybe 150 examples, the in-domain model is catching up, but we should not generalize this to like systems with more features, it would be really interesting to see what happens with more features. Maybe we will see a different behavior, that the in-domain model needs much more data to catch up, or the global model.
Okay, thank you. Let's thank the speaker again.